If you're watching this, then I'm gone. I'm not dead. Yet.
In fact, I'm actually just fine, because over the past 7 months, I've been hard at work on a board that can spell out messages from beyond the grave. But I need people to test it. So I did the only thing I could think of. Trick my friends into being part of a zero-budget horror movie.
I need your help. It's coming. Just follow the board and it will all make sense. You're probably wondering how we got here. Well, back in January, I connected with a guy named Tyler, who is the owner of an escape room company called Escape 618. Ever since I was a kid, I have been obsessed with the way that escape rooms use technology to tell a captivating story. So when he brought up needing help with a puzzle, I was immediately intrigued. During our discourse, he gave me a challenge of my own, to create a mechanical Ouija board. That's right, no human interaction, no evil spirits, just a board and some coding. But to avoid the demonic undertones of it all, we decided to make it circular. But little did I realize that small change, along with some other unforeseen circumstances, would lead me down a 5-month rabbit hole where everything that could have gone wrong did. But before we do anything, I need to actually figure out how I'm going to do this. If the board were in the rectangular shape of a typical Ouija board, I would just use a Cartesian CNC system. And while I could just use software to convert a Cartesian motion system into a circular one, that is not the max danger way. Instead, we're going to over-engineer the heck out of this, and that starts with using a polar motion system. But in order to understand how a polar motion system works, we first need to understand how polar coordinates work. Essentially, instead of using the Cartesian plane of x and y, we instead use the radius r and the angle theta to represent the position, meaning that we will need two motors, one to control the angle and the other to control the radius. This allows us to better keep track of where things are on a circular board. The idea is, if I build the whole mechanical system on a turntable using a Lazy Susan bearing, and then have a stepper motor to turn the bearing with a timing belt and a multiplier wheel, then I can put a linear actuator on top and an electromagnet, and it should just all work. It sounds simple, right? Wrong.
But with only a concept of a plan in mind.
I ordered everything on Amazon. Then I got to work on this 30-second montage. I got it all put together and finally turned it on.
I fear it did not work.
This awful noise is stemming from the belt skipping.
In retrospect,
Probably should have seen this coming. It all comes down to the physics concept of torque. Without diving too deep, the idea is essentially that it is easier to push on the rim of a wheel than it is to push somewhere closer to the center, like here. The same concept applies to resistive forces like friction, and this bearing has a metric butt-ton of friction. Unfortunately, a butt-ton is not a quantifiable unit, so we will need to make some measurements. Luckily, this is pretty straightforward. All you have to do is hook a force gauge to the outside of a turntable and pull until it moves. Then, with some math, we find that the torque of friction acting on the bearing is about 0.588 Newton meters. But the belt isn't on the outside of the wheel. It's much closer to the center. So accounting for that, we find the minimum force that needs to be applied to the wheel to make it spin is about 42 newtons, or around 9.44 pounds of force. While 10 pounds might not seem like a lot, when it comes to a motor that weighs less than a pound, 10 pounds is a tall order. But there's a way to cheat this. All we have to do is increase the radius of the wheel. So I found a pulley that is 2.5 times larger, because famously, bigger is always better. This gives us a required force of 3.66 pounds, which is within the realm of possibility for the motor. But while this math is objectively so much fun, I only have a few days left before I leave for spring break. So I had the new part sent to my home back in Illinois and packed up my project to work on it at home. Famously, not everything works the first time, so I bought more things from Amazon to try to make it work. And here is the haul. This is the reason why I made this order in the first place. We're converting to big boy belt. While this board might look great, it could use some improvement, mainly in making it compact and to make sure wires don't just fall out and break the whole thing. So we're going to convert it to one of these perf boards. Well, it's many hours later, and I finally have a finished circuit board, ready to test. So it's one day later, and I finished soldering, or so I thought. Because despite having all of this put together now, I realized I missed a wire for the electromagnet. So now I have to take this all apart and solder that one wire in. All right, I'm thinking that this is going to work. We have a few issues. One, this MOSFET's not the right one, so the electromagnet's always on and will not turn off. Definitely wired this electromagnet backwards. You know, it would be really funny if I made a mode on this that could switch the polarity, that could like yeet it. So like if it's the wrong piece, I don't even know how to detect that, but you had an RFID in it and you could reverse the polarity and then launch it. I think that could be really funny. So if I wanted to say hello with H-E, computer's way faster this way. This here is called a slip ring. Essentially, it is something that can freely rotate the wires, and with a rotating mechanism, kind of helpful. Oh, it's been a long one. I have made quite the mess, and I've made some decent progress. However, it is broken in many ways. Turns out this bearing is trash. Probably should have expected that given that it was a $37 bearing. I thought I could just solve it by putting some lubricant in there. I doused it. And then I was like, oh, there must be something in there that's slowing it down. So then I took out all of the balls in the bearing, and that's when I noticed that it's not actually perfectly round. I did get everything mounted in here. I do have the indicator wheel that goes on top of this. In theory, this is the entire stack of things. But as I said, it might seem like it could work, but it in fact doesn't in reality. I've spent at least 60 hours trying to get this to work. I'm like $600 deep into this project, and I don't really want to give up now.
Several weeks later.
Okay, after suffering for 4 weeks, the motion control works now. The code, however, leaves much to be desired. We're now entering the dreaded integration hell, where nothing works and you contemplate all your recent life decisions. There are so many things that went wrong, but here's a brief sampler. For a while, I couldn't get it to spin in the right direction, and then it was skipping letters. I kept struggling with MOSFET and eventually just gave up and bought a relay. And I also burnt my chin with the electromagnet. But by far the largest problem had to do with the paths. Let me explain. Right now, when the board needs to move between letters, it takes a direct path, which means that if it's going from A to T, it's gonna just yeet over all of these letters, which is going to give people the impression that some of these letters are also being indicated. That's not what we want. So to fix that, I wrote a pathfinding simulation. I don't know much about graph theory, so my strategy was a recursive search that explores every possible path and picks the shortest of them. This turned out to be staggeringly complicated in of itself. Once I got it working, I wrote a method to output to a binary file and loaded it on the microcontroller. I told it to go through the alphabet, and I fear it got a bit confused. So it turns out I was an idiot and forgot how polar coordinates work. So once I decided to lock in, I finally got to watch it actually work for the first time. Low-key, I could watch this thing for hours. And have watched this thing for hours. It's just kind of mesmerizing. Admittedly, it's kind of useless. So, naturally, I manufactured a reason for it to exist.
Where's Max?
Guys. while this project may not have any real practical applications, it did serve as a pretty good learning experience. So here are my 5 takeaways. First, start with a clear plan. When I started this project, I had no idea what I was doing and ended up remaking every part multiple times before I decided to actually make a real plan. Second, make it work first. Don't try to do every aspect at the same time. It's not going to work, trust me. Third, use your resources. I was trying to reinvent the wheel, literally. If I would have just asked for help earlier, it would have saved myself a lot of time. Number 4, not everything needs to be perfect. I spent way too much time trying to fix small bugs that realistically did not matter in the code, and I wish I wouldn't have done that, because then I could have just gotten the video out sooner. And finally, number 5, don't overcomplicate it. I should have just used a Cartesian CNC. It would have worked just fine and would have saved me time, energy, money, all of the things. Instead, I decided to make it overcomplicated for myself because I thought that would be cooler. And it was, but it was not worth it. So while this may not have been the most productive project, nor the most financially responsible, it did teach me a lot. And who knows, maybe this project will one day land me my dream job. But for now, I'm just glad that it's finally working. When you're curious, you find lots of interesting things to do. And curiosity is one thing that no one can ever take away from me. Thank you so much for watching, and to everyone who helped me bring this video to life. If you're looking for more of my content, maybe watch my last long-form video or follow me on Instagram. Please consider liking this video and subscribing. Thank you, everyone. I'll see you again when the dust settles from this monstrosity.